Hello, AP Physics students. This is Mrs. Armbruster. I am very unfortunately homesick. I know we've only had a few weeks of school, but I hate being homesick. But believe me, you don't want me around you. I'm going to go over the examples we would have done in class today, and actually I'll do a few more. If you want to follow along, which I would highly, highly, highly recommend, please find the kinematic equations notes. And you'll first see a video about a backwards bicycle. Watch that if you want. But we're just going to kind of jump in. I'm going to do the first two examples kind of slow. And then after that, I plan to go faster. But feel free, pause me, slow me down, rewind me, whatever you need if you need more time. So these kinematic equations are the first three equations on your equation sheet. They're also the longest three equations on the entire equation sheet. It's the worst algebra we have to do of the year. If you can do this algebra, you can do any algebra I'm going to throw at you. And these kinematic equations are made up of 6 variables. The cool thing about them is if you know any 3 of the 6, you have the information needed to find the rest. So those 6 variables are initial position, final position, initial velocity, final velocity, acceleration, and time. The variables, you'll notice a lot of them have these little subscripts by them with like a 0 or an x0. They're not a new variable, it's just a way to designate initial or final. If you came from regular physics, in that class we use I for initial and F for final. Makes a lot more sense to me. Feel free to keep using that. But the College Board uses this notation, and that's what they give you on your equation sheet. So we just kind of deal with the not as user-friendly notation in this class. So as a reminder, x0 means initial position. X means final position. Vx0 is initial velocity. Vx is final velocity. A is acceleration. And T is time. It's also helpful to think about the units. Position has units of meters. Velocity has units of meters per second. Acceleration is meters per second squared. And time is seconds. Then we have these 3 equations. We'll do a lot with them, all year long, but we're going to do a big lab connecting the graphs we did last week and the equations we're going to learn today. For your class, that'll be next week. And on your quiz that you're going to have next class, I am still planning to give you the quiz. We will spend about half the class reviewing, answering questions. I promise I'm not going to just throw you into the deep end. You'll be okay. You have one of these problems, and it's not one of the hardest ones. It's one of the easier ones on your quiz on next class, so Thursday for you guys. The first equation says final velocity equals initial velocity plus acceleration times time. The second equation is a long one. Final position equals initial position plus initial velocity times time plus 1/2 acceleration time squared. Third equation says final velocity equals initial velocity. Final velocity squared equals initial velocity squared plus 2 times acceleration times your change in position. Final minus initial. I also think it's helpful when you're looking at these to get an idea of, sure, there's a lot of variables in here, but what variables aren't? When would this equation not be useful? So this first equation has no x's, no positions. If you know something about position, try not to, probably can't use the first equation. The second equation has no final velocity, and the third equation has no time. We're almost to start our examples, but first I want to point out some key words that aren't a number, but they're telling you something about that initial position, velocity, whatever. So first thing is anytime it gets on Earth and it gets thrown up or dropped, we consider that object to be in free fall. Everything in free fall has an acceleration of, we're going to assume negative today. We'll talk about some special cases as we go along through the class. Negative 9.8 meters per second squared. This is the acceleration due to gravity. This is something that you'll probably accidentally memorize, but you don't have to memorize. They give it to you on the equation sheet. And then some words that cue you into velocity are anytime it talks about stop, at rest, that's probably it, or starts from rest. That means that your velocity is 0, either at the end or the beginning. Another thing is to keep in mind is almost always, not always, but almost always, either the final or the initial position is 0. We'll do some examples of why it could be different scenarios, but almost always one of your positions is 0. This is a problem-solving strategy that I'm going to use a lot this year. If you like it, use it. If you don't need to think about it. And you don't have to lay it out as carefully. But I'm going to use this on all of these examples we do today. Where first I'm going to identify my givens, then look for what I'm looking for, what's my unknown. Then I will choose an equation. I'm going to try really hard today to do the algebra, solve the algebra before I substitute in numbers. That's the College Board Way's preferred way of problem solving. They won't take off points, but they prefer you, and they'll give you more partial credit if you solve with variables in case you accidentally make a mistake. So that's kind of what you're going to see me practice a lot this year. Okay, here is our first problem. How long does it take a car to cross a 30-meter wide intersection after the light turns green if the car accelerates from rest at a constant 2 meters per second squared? Okay, first I almost always start these with a little sketch. I am not a good artist, but here's my intersection. Here's my bad car. That intersection is 30 meters wide. I'm trying to accelerate 2 meters per second squared. Then what I do is list out my variables. I have initial position, final position, initial velocity, final velocity, acceleration, and time. The first number I was told was 30 meters. Hopefully in your head you can think meters means position, and then you have to choose a reference frame. We'll talk about this a lot next week, but a reference frame that would make sense for this problem. In this case, I'm going to say I started at a position of 0 and ended at a position of 30. They also told me I was accelerating at a constant 2 meters per second squared, and that I started at rest. Rest means my initial velocity is 0. The question here is how long will it take? How long is a time question. So then what I have to do is look at my 3 equations and see which one would make the most sense. In this case, it's going to be the second equation. If you choose the wrong equation, don't panic, you just try again. Next thing I do is look for things that are zeros. In this case, that's my initial position and my initial velocity. So those terms will cancel, and this long equation turns into a simpler one. Then I'm trying to find time. I'm going to isolate the t. This is where, remember, we have people from Algebra 2 all the way through Calculus. You're all bringing a different amount of math in. No matter how hard this is for you, you're normal. I'm going to multiply both sides by 2 and divide both sides by acceleration. So this will say 2x over acceleration equals time squared, or time is the square root of 2x over acceleration. Then I can plug in 2 times 30 divided by 2. So this answer is going to be the square root of 30 seconds. I do not have my calculator with me, but you guys can put it in and figure it out. Okay, here's our next example. Suppose that a penny is dropped from a tower 70 meters high. So here's my tower, and here's my penny, and it's 70 meters high. What will be the speed of the penny just before it reaches the ground? When I'm setting up this one, I would try to list out my variables: initial position, final position, initial velocity, final velocity, acceleration, and time. In this one, the reference frame I'd be most likely to choose is to say that it starts 70 meters off the ground and it lands on the ground. This one has a few clues of other things that were given. The first is that word dropped. Anytime something's dropped, its initial velocity is 0. It wasn't thrown, it was just dropped. And then we're going to assume that this tower is on Earth, so acceleration is negative 9.8 meters per second squared. We're trying to find the speed of the penny when it hits the ground, so that's my final velocity. As a reminder, final velocity and speed are a pair. Velocity can be positive or negative. Speed's always positive. So if you find velocity, you found speed. Sorry, I'm not trying to yawn as much as I am. I'm trying to find time. Not trying to find time. I don't have time, so I'm going to use the third equation that doesn't have time. Then I'm going to look at my zeros. Well, my final position is 0, and so is my initial position. So this simplifies to final velocity squared equals 2 times acceleration times negative initial position. Now, I guess I could isolate the final velocity by taking the square root. And now I'm going to plug in and solve. So final velocity equals the square root of 2 times negative 9.8 times negative 70. Those two negatives are important. They turn it into a positive. And then, again, sorry that I don't have a calculator, but you would end up getting whatever that is would be your final velocity. Okay, now we've got an eagle. We've got a bald eagle flying to the left. Here's my eagle flying to the left with a speed of 34 meters per second. When a gust of wind blows back against it, isn't that a great wind, at a constant acceleration of 8 meters per second squared. What will be the speed of the bald eagle after the wind has blown for 3 seconds? Okay, this one's important because the velocity and acceleration are pointing opposite directions of each other. You could, my 8A decided this 2 different ways. One option is you could say that since the eagle's flying left, that it's flying with a negative velocity and a positive acceleration that's going to the right. Or you could say the eagle's traveling with a positive velocity and has an acceleration that's negative and slowing it down. Either way, there has to be a sign difference between the velocity and acceleration. You'll get the same answer either way. It's a cool thing and an annoying thing about physics. But I'm listing my variables. The initial speed of the eagle is 34 meters per second. Its acceleration is negative 8. Again, you could flip those and you'd still get the same answer. The wind's going to blow for 3 seconds. We know nothing about how far it's moved, but we can still find that final velocity with the first equation. I'm looking for final velocity. I don't have to do any algebra. I've already isolated that variable. Equals 34 plus negative 8 times 3. This I could actually do in my head. 8 times 3 is 24. 34 minus 24 is 10 meters per second. Okay, 2 more. This one's a 2-step problem. There's one a lot like it on your class kick, except I took out the hint that you first need to find acceleration before you can find distance. So, but that's very similar to one of your class kick problems. Sorry. We've got a car accelerating from one speed to another in 4 seconds. So, I guess, maybe I won't draw a car. I think we can kind of picture that, hopefully. I'm going to list out my variables. It's going from 16 meters per second to 36 meters per second in 4 seconds, and I'm looking for acceleration and distance traveled. We're also going to need to define an initial position. When in doubt, initial position is 0. The car had not moved relative to its spot before the 4 seconds. Okay, to find acceleration, I'm going to use the first equation first. Final velocity equals initial velocity plus acceleration times time. 36 equals 16 Oh, I started plugging in numbers. Hang on, I'll be good. I'll do my algebra first. Sorry. Okay, I'm trying to isolate acceleration. So first I'm going to subtract initial velocity from each side. Then I'm going to divide both sides by t. And I've solved for my unknown that I'm looking for. So acceleration is going to be 36 meters per second minus 16 meters per second divided by 4 seconds. Here's another one I can do in my head. 36 minus 16 is 20. 20 divided by 4 is 5 meters per second squared. Okay, there's the acceleration of the car, and then part 2 was and the distance traveled. You could use either of the final equations. I'm going to use the second one because it's less algebra I have to do, like manipulating variables. I do have a 0, my initial position, but then I'm going to have to plug in x equals 16 times 4 plus 1/2. Now I know what my acceleration is, times 4 squared. Okay, check my work because you can probably tell, not myself, but 16 times 4 I'm pretty sure is 64. 4 squared's 8. Half of that is 4 times 5 is 20. No, what did I do wrong? 16, 8. 8 times 5 is not 20, it's 40. 64 plus 40 is 104 meters. Okay, last question. This is a lot like the practice assignment for today. So here's the scenario. And I know some of your phones are like fancy and waterproof now, but we're going to just go with this. You drop your cell phone. There's your phone, your little iPhone. While in the bathroom in front of the mirror while the water is running in the sink. Okay, so here's the sink. And here's the water. I'll make it blue. I'll be so fancy. Okay, pardon my bad art. You are 0.45 meters above the sink. How long do you have before your phone is a goner? What I mean by that is till your phone goes swimming in the sink. Some of your phones would have no problem, but back in the day it was quite the travesty. You had to get out rice and the whole thing. It was terrible. Okay, if I'm going to do this one, I'm going to set up my variables. The only number I was told was that you're 0.45 meters above the sink. In my head, what I would do is do 0.45 to 0 for my initial and final position. You could also do 0 to negative 0.45 because you fell down that many meters. You dropped your phone. You did not throw it, you dropped your phone. So its initial velocity is 0. And we dropped our phone on Earth where acceleration is negative 9.8. Oh, I'm being bad with units. And we're looking for how long do you have to catch your phone. I don't have final velocity, so that's going to lead me to that second kinematic equation. Xt squared. Let's look at my zeros. I don't have an initial or final position. I don't have an initial velocity. 0 equals x naught plus 1/2 a t squared. I'm trying to isolate the time. So first I'm going to subtract initial position. Then I'm going to multiply by 2 and divide by a. Negative 2x naught over a equals t squared. T is the square root. Negative 2x naught over a. Then I could plug in, again, I'm sorry, I'm going to leave it as a expression because I can't do all of that in my head, especially today. But negative 2 times 0.45 divided by negative 9.8. That's going to, the negatives will cancel, so that's solid. But that'll be, it's like I would say 0.4 seconds, something like that. Here is your optional practice assignment for the night. You do not have to, don't worry too much about all the words in here, unless that helps you, then you can. But essentially what you're going to do is work with a partner and have your partner hold a ruler or a meter stick My rulers are on the front corner of my table, and my meter sticks are in that cabinet by the TV. And they're going to drop it while your hand is open at the bottom of the meter stick. And then you are going to measure how far the ruler or meter stick travels while you react and catch it. And you're going to try it twice, once when you're focused and once when you're distracted. What you'll do, I'm going to give you guys a little bit of a boost because I'm gone, so I can't help you in person. But if I list out those variables, you're going to drop the ruler. You are going to let it fall because of Earth. I would probably, maybe for like negative sake, make it have a final position of 0, and this is what you're going to measure. But here's an important pitfall where you'll think that you have a terrible reaction time. Turn your centimeters into meters by dividing by 100. But it should be a pretty fast, pretty fun. You can see who's the fastest reaction time in the class. I am suggested try it focused and try it distracted so you can think about how that connects to distracted driving. But you can do that, and then when you get done, there is a new class kick assigned. The class kick is not due until next week, so I'll be able to answer any questions you have. Your class kick that was supposed to be due today, I will check it off tomorrow morning, assuming I'm back at school, and I will grade with as much grace. Just try to get it attempted by the end of the class today, and I promise I'll grade with grace because I know this is not ideal and you did not choose for your physics teacher to be sick today. Hope you're having a great day and hope I'm feeling better too. See you, I very, very, very much hope, on Thursday.